It is a privilege that we get to have Phil here today. For those of you who don't know, this is Phil Chodrow. He's a PhD student in applied mathematics and other things at MIT, but has been really focusing in and doing some really nice work on network science, and specifically lately he's doing a lot of more on the statistical inference side of networks. And you might have seen recently he published a nice thing on Archive called Configuration Models of Random Hypergraphs and Their Applications. And he's going to yell at us about it today. So, thank you.
Okay, so I'm going to attempt to speak at a normal indoor projection to multiple people, but not overdoing it voice, about configuration models of random hypergraphs and their applications. So thank you all for being here. Thank you to Brennan for putting this on, and of course the Institute for making it possible and giving us this space. So I'm Phil Chodrow. I'm from MIT. I think many, at least half of you, we've actually chatted before, so that's enough introduction. So I want to talk today about configuration models of random hypergraphs and their applications. And this project, while there is mathematical content to it, really has a data scientific kind of motivation. And so I want to start with the data here. I think all of us have heard about, and many of us have probably actually worked with, what I'm going to call polyadic networks. So these are sometimes called higher order networks. I don't like that because that's like calling 3 a higher order number, and I think that's silly. So I'm going to refer to these polyadic networks. These are networks in which we allow arbitrary numbers of entities to interact simultaneously. So we see these all over the place. Collaboration networks in which a node is an author and an edge is a paper, or a node is a sponsor and Congress and an edge is a bill that they've all co-sponsored. Co-presence networks, you just track whether everyone is in the same place or close enough to the same place at the same time, so we could all have an edge between us right now. Communication networks, different kinds of permutations here, emails, forum threads. As you know, there are lots of ways to define what's the node and what's the edge, but the point here is that many of the ways we'll do this across a wide variety of domains are naturally modeled in which we allow edges to have more than 2 nodes. So polyadic networks are all around us, they're in many of our data sets, and historically, what we've often done is to represent them dyadically. So you might see, for example, here's a pretty famous illustration of a Santa Fe Institute collaboration network. This is in a paper by Mark Newman, who I hear is coming in the near future. So this is a dyadic representation of some data that's natively polyadic, right? And there's good reason to do this because we have all these fantastic algorithms for working with dyadic data. When you represent your polyadic data dyadically, you can then apply all your great algorithms, inference, community detection, clustering coefficients, any metric you want. You can just bring all that theory in and apply it to this polyadic data set without doing any additional work. So that's very attractive, and it's something that a lot of researchers have done over the last 2 decades. It's something that I have done as well. That said, I want to convince you of essentially 3 things today. So the first thing I want to convince you of is that applying dyadic graph techniques can produce unreliable results on polyadic data sets. So proceed with caution. I'm not going to tell you never do this, but proceed with caution and make sure that you're very clear about what's going on. Second, I am going to argue to you that whenever possible, we should instead use natively polyadic metrics and models. So we should be aware of the polyadic nature of our data, use polyadic data structures to model it, and then use polyadic metrics that we use to measure aspects of those structures. So that's the second thing I'd like to convince you of. The third thing I'd like to convince you of is the following. When we do this, and in particular when we use random hypergraph null models, we can get some new perspectives on some conventional wisdom in network data science. So we'll actually see some old accepted results, for example, that social networks are clustered, or that social networks display degree assortativity. We're actually going to see a little bit of a contrarian point of view on some of these very old kind of established ideas in network science through the use of random polyadic nulls. So that's the agenda for today. I'd like to start with everyone's favorite party game, which is this data set degree assortative? I go to great parties, let me tell you, I go to the best parties. Okay, so I have a data set here, let's call it a collaboration network, okay? So there's one paper that has 6 authors, can count. Applied mathematicians can count sometimes. One paper with 6 authors, and then 2 papers, each of which has 2 authors. this node here has been involved in 2 of the 2 author papers. Everyone else has been involved in only 1 paper. So I'm going to give you 5 seconds, okay? Think about it with all of the great gravity that this important scientific question deserves, and I'm going to ask you, is this data set degree assortative? So 5 seconds, think about it, go. Okay, hands if you think this data set is degree assortative. Okay, 1 person. 2 people, 3 people, okay. Hands if you think this data set is degree disassortative. Okay, 1 person. Hands if you think it's kind of neither, it's roughly 0 assortativity. Okay, that seems to be a majority. Hands for, I don't know. Okay, that's actually the new majority. And hands for it depends. Okay, yeah, so I think a few people might have voted twice, or 3 times. But that's okay. So, of course, I hope this is relatively predictable. The answer is it depends, right? And I'm going to argue to you that it depends pretty strongly on how we choose to model this data. But in order to motivate that, I want to be a little bit more precise about what question we're actually asking here when we say, is this data set degree assortative? So, I claim there are basically 3 components that are involved here. So, first, we are asking, is the observed data more assortative? We need a measure of assortativity. By degree, we need to define degrees, than would be expected at random. And for at random, we need a null model. So there are 3 mathematical or modeling decisions that we need to make in order to actually go after this question. So again, we need to define a measure of assortativity, we need to define a data structure that will tell us what the degrees are, and we need a null model that's going to be our comparison. And if our result is larger than what we would expect under the null model, we'll say it's statistically significantly assortative. So from our basic question, is it degree assortative, we now have 3 mathematical decisions to make. I'm going to outline to you a historical way in which these decisions have typically been made, and then we'll talk about some issues we could possibly have with that approach. So a very classical way to define the data structure and implicitly define the degrees is the projected graph. So when we do a projected graph, right, we are going to take each edge of any dimension and we're going to replace it with a clique of dyadic edges, right? So here is a 6th edge on the right. We're going to bring it over here, project it. By projecting it, we replace the 6th edge with a 6th clique that now has 15 dyadic edges in it. And the result is that we now have a projected graph. It's a dyadic graph, and that's implicitly what was in that Newman visualization earlier, right? We get out of this a graph where all edges have 2 nodes, and we can play all our familiar games. So that's our data representation. Note that implicitly this gives us an answer for what the degrees of the nodes are, right? Each of these nodes in this edge has 5 connections to each of its other co-authors, so the degrees are going to be 5. Degree 2, degree 1, degree 1.
Did we not make a clique out of the HIJ subgraph?
Yeah, so 2 cliques are in fact just edges. Yeah, so there's 1 2-edge here, 1 2-edge here, and each of them is actually its own clique. Oh. Okay, there we go. So next decision we have to make is how to measure assortativity. So we're going to use today the Spearman assortativity coefficient. Some of you may have used the Pearson assortativity coefficient and seen it used at other places. If you don't know why you should use the Spearman assortativity coefficient instead, ask him. He's around here somewhere, and he wrote a really lovely paper on this. It was news to me about 2 months ago, and I encourage you to read it and learn why to use the Spearman coefficient. So we're going to use the Spearman assortativity coefficient. We are going to compute the correlation coefficient between the ranks of nodes by degree. Not the degrees themselves, but the ranks of nodes by degree. Still get a correlation coefficient. And you can naturally understand this correlation coefficient is asking the following kind of question. Do nodes with many neighbors tend to disproportionately connect nodes with many other neighbors? It's just a linear correlation coefficient, so everything you know about linear relationships, linear regression, kind of works here as well. If you do this on the projected network we just computed, you'll find that the Spearman assortativity coefficient for that toy projected network is 0.99, so it's almost the largest it can be. Questions so far? Comments, concerns? Okay, we needed 3 elements. We needed to set the degrees, we needed to choose an assortativity measure, and we needed to choose a random null model, so that's the next step. We are going to consider the dyadic configuration model, okay? So This is closely related to the configuration model that we learned about in Network Science 101. We're going to fix a degree sequence D, and we're going to define a space of graphs. The space of graphs is simply the set of all graphs that share that degree sequence, okay? Then, by definition, the vertex-labeled configuration model is the uniform probability distribution on that space of graphs. So it's saying every graph that has that degree sequence is equally likely. Now, if this doesn't look to you like the configuration model that you know and love, you might be expecting something related to stub matching, then I really encourage you to read this beautiful paper by Fosdick, Larimore, Nishimura, and Ugander that just came out in SciAm Review on the differences between different configuration models and why it matters. Stub matching, stub-labeled configuration models are closely related to this vertex-labeled configuration model in the asymptotic limit. However, we're actually going to be doing some work in places where we're definitely not in the asymptotic regime, which is why we're being careful here. I really recommend this paper. It's a lovely paper. Please read it. Okay, so now we have all three elements that we needed. We are ready to do hypothesis testing. So what are we going to do? We are going to take our data set of interest. We're going to measure rho, the empirical assortativity coefficient. We're going to pull many random samples from the null distribution that we care about, in this case the vertex-labeled configuration model, and compute rho on each of those. And then we'll check the observed value against the sampling distribution. And that's our statistical test. We can see, well, is it within the bulk of the sampling distribution? Is it way over to one side? Is it way over to the other side? And that's our hypothesis test. Questions about the statistical game? Okay, so when we do that on our toy data set, the result looks a bit like this. So each of these are sampling distributions. I've done both the stub-labeled configuration model that you might be familiar with, as well as the vertex-labeled configuration model that I defined as the uniform distribution over these graphs. And if you do either model, they say, well, the null value of the assortativity should be around 1/2 or so, with a little bit of variance out here. You see these sharp truncations just because this data set is so small. And if we compare that to the 0.99 that we measured earlier over here, we would say, okay, well, this toy data set is very statistically significantly degree assortative. Okay, so this is a fairly historically classical approach to dealing with polyadic data. We have projected it, we've compared it against a dyadic null model, and we've gotten an answer. Okay. I would now like to encourage you to be troubled by this in the following ways. So, first of all, let's kind of go back to why we care about degree assortativity in the first place. So, in that lovely paper by Fosdick and collaborators, they note the following. Degree assortativity is common in social networks, and collaboration networks, for example, are commonly thought to be no exception due to collaborations between extremely productive researchers. So the scientific content of degree assortativity here is supposed to be about relationships between extremely productive researchers. Now, it's worth checking whether our approach here actually is in line with the scientific content of what we are aiming to measure. So when we think about this projection operation, we notice a couple things. So first of all, if you think that each person contributes equally to one paper and that one paper costs 1 unit of effort, actually the highest degree nodes in the projected graph are the least productive researchers because each of them wrote 1/6 of a paper. However, they're treated in the projected graph as if they all wrote 5 papers. So that's a bit, let's say, worth tracking and worth keeping track of when we consider what this measurement means. Second, when we compute the assortativity coefficient, we average over edges in the projected graph. That means that this clique is going to get counted 15 times because it has 15 edges, while each of these papers are each counted once. So this paper, this one paper over here, is now actually accounting for 15 times as much weight in the calculation of the assortativity coefficient as either of these guys. Again, I'm not going to say that's always wrong, but please be aware that that's what's going on when we do this kind of calculation. Then, finally, randomization, okay? When we compare to a dyadic configuration model on this projected graph, what we are comparing to is not a world in which there's one paper with 6 authors and 2 papers with 2 authors. We're comparing to a world in which there are 17 papers with 2 authors. There are no multi-author papers in this world of counterfactuals. There are just pairs of people writing 17 papers. So this especially should be a little bit troubling, right? Because it doesn't really resemble even a boring version of the world that we actually live in when it comes to collaboration networks. So if you're modeling a world in which only 2 author papers are allowed, you're going to be surprised by an awful lot that I'm going to argue later shouldn't necessarily be that surprising. So taken together, I hope to have convinced you that in this particular case at least, dyadic hypothesis testing produces a distorted measure of assortativity and compares it to a pretty irrelevant null distribution. Questions, comments, concerns so far?
Why the representation on the left? That ring on the left, on the far left. What, is that supposed to be like a network? Is that just a...
This is just a single paper that 6 people wrote.
So why wouldn't it be represented already as a clique?
So it's not that you can't do that, it's that that's a choice. You don't have to.
Because that's a perfectly assortative network on the left. Every node has degree 2, and every node of degree 2 is connected to another node of degree 2.
Oh, sorry, it might be that these edges I put on it were misleading. So if you want, you can ignore the outside boundary here. It's just one paper that 6 people wrote.
Okay.
Yeah. So recall the things that I wanted to convince you of today. The first thing I wanted to convince you was that dyadic graph techniques can produce unreliable results on polyadic data sets, and I hope to have given you a very simple illustration of that claim already. The next thing I aim to argue for you is that we should instead use natively polyadic metrics and models, and that brings us to our next section. So the title of this talk was, of course, Configuration Models of Random Hypergraphs, so let's actually talk about that. First, let's get into hypergraphs, just a quick review. So a hypergraph consists, much like a graph, of nodes, a vertex set V and an edge set E. The thing to know about E is that it's no longer just a set of pairs of nodes, it's a set of multi-set of sets of nodes. And what does that mean? It means edges can have any number of nodes. 2 is fine, 3 is fine, n is fine, where n is any finite non-negative integer. Even 1 is actually fine. It doesn't turn out to be all that useful most of the time, but one node edges are just fine. What we are going to rule out are degenerate edges. So a node can't be part of the same edge twice, essentially is what that says. You can think of that as we're not considering self-loops in the graph. These kinds of degenerate edges correspond to self-loops in the context of dyadic networks. We're not going to let any nodes belong to the same edge multiple times. Parallel edges are absolutely okay. In context, I hope this looks like a very natural way of modeling things like collaboration networks, right? So a paper can have any number of authors greater than or equal to 1, and the same group of authors can author multiple papers, is essentially what's going on here. So I hope this feels like a very natural data structure for this kind of data set. Now, we have a data structure. We still need a null model over that data structure. We can get some inspiration from the dyadic null model case. So to get to configuration models for hypergraphs, recall that in the context of dyadic graphs, we're going to observe a given graph with a degree sequence, and then we're going to take a null space with all graphs that have that same degree sequence. In the context of hypergraphs, we're just going to add an additional piece of information to our null space. We're going to observe a hypergraph with a given degree sequence and a given edge dimension sequence k. So the edge dimension sequence says, well, there was 1 paper with 6 authors and 2 papers with 2 authors. That information is getting stored as well. Not only do we know how many papers each author has written, but we also know how many authors each paper has. We're not collecting who's authored which paper, we're just collecting how many are on each. So our null space that we define is now the set of all hypergraphs that have the same degree sequence d and edge dimension k. So nothing magic here, we've just defined a uniform distribution over a slightly more structured space where we've included information about the sizes of the edges. For those who want to see something a little bit more mathematical looking, we'll define a null space, v sub d and k, which is the space of all hypergraphs with the specified degree sequence and edge dimension sequence. And by definition, the vertex labeled configuration model is the uniform distribution on this space. Remember, we also have this stub-labeled hypergraph, or sub-labeled graph model floating around, which is the Network Science 101 version of the configuration model. We can do that in the context of hypergraphs as well. If you are interested in that, there are details in the paper that I'll try to sell you on at the end of this talk, but I'm not going to talk about that too much more here. Okay, so next mathematical detail to figure out. We've defined a probability distribution over a space of hypergraphs. We now need to show that we can sample from it. If we can't sample from this probability distribution, we're not going to be able to construct sampling distributions of statistics. We're not going to be able to do hypothesis testing. So we need to be able to sample. We can't do stub matching. It's not going to work in this context because of how we've defined this space. So we need to do something else. And what we can do is we can systematically crawl through the space of all possible hypergraphs that we care about in a stochastic but structured way, such that we're guaranteed to approximately sample from the correct distribution at the end. This is the idea of Markov chain Monte Carlo, and so we can define a Markov chain Monte Carlo algorithm to sample from this space. What we're going to do, in words, is we're going to start with an initial valid hypergraph in this space. A good one is just the original data, actually, to start with the original data and then randomize from there. Then, for as long as you like, grab 2 edges at a time and shuffle them together. Essentially, exchange nodes between them in such a way that you preserve the size of the edges, but otherwise just randomize all the nodes between them and call that a day. That's going to give you a proposed new graph that's very similar to the old graph. It differs only in 2 edges, but it's a proposed new graph. And we're going to accept that proposal with a certain probability that's related to the multiplicity of those edges in the initial state. So remember that parallel edges are allowed, so we need to track how many edges are parallel here. We get a proposal. If we accept it, then we now have a new graph. That graph is the next state. We're going to do this for many thousands or millions or billions of iterations. And if we return the state at regular intervals of sufficiently long length, we will provably theorem sample asymptotically from the vertex labeled configuration model. So this gives us an algorithm for actually pulling out hypergraphs that are distributed according to this model. Okay. So we had some motivation related to unreliable results using dyadic techniques on polyadic networks. We now have a new model, this hypergraph configuration model. We have a definition of it, and we have a provable algorithm for sampling from it. So we actually now have everything that we need in order to do some data science using this model. So recall that what I've been trying to convince you of this whole time is that dyadic graph techniques can produce unreliable results on polyadic data sets. We should instead use natively polyadic metrics and models. I've given you a model now, and we're going to define some metrics when we get to applications. And as we find those applications, I'm going to argue to you that we get some new perspectives on conventional wisdom in network science when we use these random null models. So with that in mind, let's dive into 2 applications in which we're going to revisit some pretty classical results in network science through the lens of these hypergraph configuration models. So before I jump into these applications, I'd like to first say thanks for the data to Austin Benson and his collaborators on this lovely paper, Simplicial Closure and Higher Order Link Prediction. If you go to Austin's website, you'll find time-stamped polyadic data sets in a number of different application areas. Emails, drug co-occurrence, congressional co-sponsorships, academic co-authorships, forum threads, and more. I'm not using the timestamps today, but they are timestamps. You can actually have a lot of fun with this data. If you're interested in polyadic data sets, polyadic data science, and you need some data to play with, check it out. It's a lot of fun. And also read this paper, because it's a great paper. Oh, yes, good. I see a picture being taken. Excellent. Okay, so yeah, read that paper. It's lovely. Okay, so let's start with assortativity. This was our motivating example from earlier. So part of why we got into trouble in assortativity using our dyadic methods was because the dyadic assortativity coefficient was actually asking a question which was a little different from our intuition about what assortativity should mean. The dyadic assortativity coefficient asks whether authors with many collaborators tend to co-author with other authors with many collaborators, right? Because each edge doesn't represent a paper, it represents a co-authorship relationship, right? So the assortativity measure in dyadic space means something a little bit different than what we might expect. On the other hand, we had this sort of folk theory about assortativity that we talked about earlier. Do authors of many papers, so extremely productive researchers, tend to author with other authors of many papers? So we can actually get at that second idea quite naturally through a polyadic framework using hypergraphs. So the first thing we need to do, remember 3 elements. We need a data structure, we need an assortativity measure, and we need a random null model. So we need a data structure, use a hypergraph. We don't actually have to transform the data at all. There's no projection to be done. The data looks like this. Each of these nodes has degree not 5, but 1, because it's involved in one edge. This node has degree 2, 1, 1. So now we are not messing with the edges in any way. We're actually just keeping them pretty much as they come to us in the data. So hypergraph representation fixes the nodes. We can use the same Spearman coefficient from before to measure the assortativity. One important thing to check here is that the averages are taken over edges, not pairs of nodes. So we are going to downweight nodes on large edges so that each edge is counted the same number of times in this formula. So it's possible to catch out these expectations in a way that makes that work, but the important thing to check here is that we are averaging over edges, not pairs of nodes, because pairs of nodes is the dyadic paradigm, and we're trying not to do that. So when we compute the Spearman coefficient, we get a pretty interestingly different result in our toy network. If we compute the polyadic Spearman coefficient, we are actually going to find that the Spearman coefficient is negative. Recall that our Spearman coefficient was almost 1 when we used the dyadic framework, and now we have not just decreased that, we have flipped the sign. It's now minus 0.25. This is an extremely dramatic example of a difference between a polyadic assortativity measure and a dyadic assortativity measure. It's especially pronounced in this synthetic case, but actually if you look at some real data, you'll find some pretty striking differences in magnitude here. So I've taken a whole bunch of data sets. These are all from Austin's website, thank you. For each of these data sets, I've computed in black the hypergraph polyadic assortativity measure, and in red, the same assortativity measure, but now we're computing on the dyadic graph. So we're essentially doing the first calculation we saw by way of comparison. There are some kind of concerning things to notice about this figure. So first of all, the relationship between these measures is not monotonic. As the hypergraph measure goes up, the projected measure might go up or down, a little hard to tell. The projected measure can be either higher or lower than the hypergraph measure. So there's quite a bit of variability in that respect. And indeed, you can even observe sign changes. So down here at the bottom, we see cases where the projected measure would be positive, whereas the polyadic hypergraph measure is negative. So this is a big difference, right, in what our assortativity measure means and what results we'll get when we apply different measures. Now, I'm not here to tell you that the dyadic version is always wrong or that the hypergraph version is always better. I am here to tell you, hey, check sort of with the science of what hypothesis you're testing and make sure that that idea is actually captured by the measure you are using. I claim that in the case, for example, of academic co-authorships, if our hypothesis is about extremely productive researchers, we really want to be using this hypergraph measure instead. And that can make a big difference in our data sets, as we can see from these results. Yeah.
Can you say a little bit about the opposite case where, like in the high school network, it looks like it lines up really well? Do you kind of have a hypothesis for why?
That's because, in the high school network specifically, almost all the edges are in fact edges of size 2.
Okay.
So
it's like face-to-face contact?
Yeah,
okay.
Yeah. There are a few of size 3, but almost all of them are size 2. Yeah. So it's a little hard to interpret these out of context, right? So is a negative value high or low? You actually have to check, and this is where we do significance tests. This is where it matters that we have a random graph null model. So we can do significance tests. Here's a set of 4 significance tests. Up top, this is the same figure we saw earlier. This is that synthetic toy data set using dyadic methods or projected methods, where we found an assortativity of almost 1 and found that that was highly statistically significant. On the other hand, over here on my left, your right, we have the same data set. Now we're using hypergraph polyadic measures. The assortativity coefficient is minus 0.25, and that actually turns out to be, depending on where you define your cutoff, this could be statistically significant in the other direction. It could be statistically significantly disassortative, depending on what level you want to be testing here. At about the 10% level, that would be statistically significantly disassortative. So really, everything can go wrong here, right? You can get things that are statistically significant in the wrong direction if you're not careful about what method you're using. This also makes a difference when we move over to real-world data sets. So this is the Enron email corpus, and where each node is a sender or receiver of an email. Each edge is an email itself. If we work with this corpus in projected space, we do the dyadic computation, we'll find an assortativity coefficient of a little more than 1/2, and under either the vertex or the stub-labeled configuration models, we'll say, oh yeah, that's statistically significantly assortative. On the other hand, if we go over to the, I claim, more appropriate hypergraph measure, we'll find, okay, well, the observed assortativity is a little bit lower, it's a little bit under 1/2 now. On the other hand, use of the hypergraph null actually significantly changes the structure of the distribution we're testing against. And as a result, the observed value falls within the bulk of the null distribution. So we would say, okay, this is nothing special. So this distinction between polyadic and dyadic methods actually can drive statistically significantly different study conclusions here. You can get statistically right or wrong answers depending on this choice. So I'm not saying that I'm going to tell you the hypergraph one is always the right one to do. I am telling you it really matters and you can get meaningfully different results. So please think very carefully about your model selection. Overall, from this little vignette on assortativity, I hope to convince you of the following. We can study degree assortativity without projections. We don't have to do dyadic projections at all if we feel that's not appropriate for a study domain. Doing this, at least in many cases, actually better matches our intuitions about what assortativity is supposed to mean, really the scientific content of assortativity. And finally, the results we get can actually vary significantly, and I mean both practically significantly and statistically significantly, from approaches based on projected dyadic methods. Questions so far? Okay, let's jump into a second application. So I want to talk about clustering. Okay, so this is another good network science 101 type of topic. Recall, the clustering idea is that roughly your friends tend to know each other, triadic closure and all that jazz. We have a nice clustering coefficient where we measure the number of triangles and divide by the number of 2 stars, or the number of possible triangles. And this measure is close to 1 when our network is highly clustered and close to 0 when it's more tree-like. Okay, so nice review here, and in an obscure paper that you might not have heard of, we heard this nice familiar story that, well look, social networks display clustering and configuration models don't, and so therefore we need a new model. And that's how we got the small world model. Okay, so quick review of clustering, not too much magic there. Let's take a look at our favorite data set again. So for clustering is a little bit special because it's an intrinsically dyadic concept, so we do actually have to project. So we're going to take our toy data set, we'll project it, we get our projected graph, and we compute the clustering coefficient. There are 6 choose 3 triangles in here. There are 6 choose 3 possible triangles here, plus 1 possible triangle here. That one is not present, and so we are going to get a clustering coefficient that is almost, but not exactly 1. So very clustered network, great. Now, clustering in polyadic networks can actually come from 2 places, right? So there's clustering that comes from within edges. We're seeing an example of that here. So this edge contains all the clustering in the graph. Specifically, this edge contains all the clustering in the graph. It's not about having 3 edges that are arranged in a specific way, it's about having 1 hyperedge just be present. So that's a kind of trivial source of triadic closure. And then, of course, there is non-trivial triadic closure as well, and that's the tendency of multiple edges to correlate with each other in ways that tend to close. So when we measure triadic closure, in this kind of case, it's very easy to tell what the source of the clustering coefficient is. It's this edge. In practical data sets, it can be harder. So we actually need to distinguish where our triadic closure is coming from and what it means in context. I mentioned that in order to do this, in any case, in order to compute clustering at all, we do need to project. And it matters when we project. So when we project before or after randomizing, we're going to get different results. Projecting before randomizing means we're going to be randomizing over a dyadic graph, and that's going to bring us back to our dyadic configuration model, same story from before. If we project after randomizing, I claim we're going to get more meaningful results. Of course, that requires us to randomize over hypergraph space, and that's what we have this nice new null model for. So we're going to randomize before and after, and we can do a little comparison. So here is a table of 7 data sets, where what I've done is I've taken each data set, I've computed the clustering coefficient, of that data, and then I've randomized it. First, I randomized it using the hypergraph null model that we've been developing. Second, I projected it and then I randomized it to compute a dyadic version of the clustering coefficient null distribution as well. So for each of these null distributions, I've given you the mean as well as the standard deviation in parentheses. Some important things to note here. Of these 7 data sets, only one is statistically significantly more clustered than you'd expect under a hypergraph null model, and that's this co-authorship geology network here. And even that, it's only just so. So the clustering coefficient for that one is 0.82, and the null expectation is 0.81. So it's statistically significant. It's very close to what you would expect by random chance. On the other hand, one data set is statistically about as clustered as you would expect under the null model, and 5 are actually less clustered than you would expect under a hypergraph null model. So not only is it not the case that there is sort of clustering over and above random chance, there's actually a negative clustering effect going on here. There's as much clustering as would be expected under the null, minus a tendency for edges to actually avoid each other in these data sets. Now, that sounds a little bit magical. I will give you a hypothesis about why that turns out to be the case in these data sets. I just want to note along the way that when we do this over the dyadic data sets, we get pretty much what you would expect. All the dyadic data sets think that the clustering coefficient should be about 0. All the dyadic models think the clustering coefficient should be about 0, which of course is the complaint of the Watson-Sturgatz paper to begin with. So why actually would we not think this result is too shocking? I have a hypothesis about this. I don't know. But my hypothesis is this. When you have dyadic social networks, in which relationships are between pairs of people, think Facebook for example, you do get this often remarked non-trivial triadic closure. In contrast, in polyadic networks, I suggest, possible triangles will tend to get absorbed into polyadic networks, into polyadic edges, sorry. So if Brennan and I are thinking of writing a paper, and Leo and Brennan are thinking of writing a paper, and Leo and I are thinking of writing a paper, not guaranteed, but there's a decent chance we have similar topics on our mind, so maybe instead of producing 3 papers with 2 authors, we're actually going to write 1 paper together, and that'll be sort of captured by this null model. So that's a hypothesis. I think there's actually a lot of good work to be done on that and kind of testing that hypothesis. So if anyone is interested in sort of doing some data science around that and trying to get to the bottom of really what we should expect in collaboration networks and other polyadic networks, I think that's a really exciting area for future research. Any questions about this application in triadic closure and clustering? Okay, so with that, let's sort of begin wrapping up. So recall that throughout this talk, I've tried to convince you of the following items. First, that dyadic graph techniques can produce unreliable results on polyadic data sets. I think that's the 4th time I've said that now. Second, we should instead use natively polyadic metrics and models. And third and finally, random hypergraph null models, such as the configuration model for random hypergraphs, suggest new perspectives and some conventional wisdom in network data science. Now, this work is very much still in development. In particular, I think there are a number of promising future methodological developments as well as future data science developments. So, one live area of research right now, lots of cool papers coming out just in the last couple of years, are around community detection methods in polyadic data sets. Now, many of you may know that our favorite community detection measure, the modularity, which is problem-free and extremely reliable in all cases, is actually founded on the dyadic configuration model. That's its sort of fundamental ingredient. If we have a polyadic configuration model, we can probably think about polyadic modularity measures, and maybe we can do something useful there. Another question that I think is very important going forward, there are cases when you actually should project into dyadic networks. When you should project, what's the best way to do it? There are choices about how to project, and I think that there's actually some good mathematics to be done to figure out what the right way to project is according to your problem domain. Finally, recall that many of our famous results in network theory, and in particular dynamics on networks, are based on essentially mean field theories based on the configuration model. So for example, epidemic thresholds and scale-free networks, that's a mean field theory based on the configuration model. It would be interesting to see how far we can bring those in the context of dynamics on polyadic networks. And I think that some of these tools may be of use in that context. All that said, I'd like to thank Patrick Jaillet at MIT for some helpful discussions along the way, the NSF for support, Brennan for putting this talk together, all of you for being here and offering your time and attention. If you like what you heard, please feel free to read the paper or reach out to me or do both, extra credit. And with that, I'm all done and I'd be happy to take any questions, talk offline. Thanks.
Okay, we have time for questions.
Just want some clarification. So in your hypergraph configuration model, when you mean degree of the node, you mean like how many edges the node is involved in?
Yep.
Not like say how many one-dimensional edges, how many two-dimensional edges.
Mm-hmm. You can define a configuration model, and I actually did this in the early stages of this project, where you'll preserve all of those pieces of information as well. That's a very constrained distribution with a lot of parameters, so eventually I decided it was a little bit less interesting. But you absolutely can do that, and it will work. I think I haven't yet seen an application area that made me think that that was the right thing to do, but if you have one in mind, let's talk.
In particular, in the case of collaboration hypergraphs, when you have nodes, routers, and edges are papers, you can also represent this as a bipartite graph.
Mm-hmm.
Can you, like, is there an equivalent definition of your configuration model for a set of bipartite graphs that is equivalent?
Yeah, so this is where the labeling issue kind of comes up. So you can do a dyadic configuration model on the bipartite graph, nothing stopping you from doing that. If you do a stub-labeled configuration model on the bipartite graph, that's going to be provably equivalent to the stub-labeled hypergraph configuration model, probabilistically speaking. You can do a vertex-labeled bipartite randomization. I don't think that there's any application areas that make me think that's the right thing to do, and that will not be equivalent to the vertex-labeled hypergraph configuration model. So that's another thing where I'd like to see the application that motivates that. It can be done.
Okay.
Yeah.
Go back to the slide about Metropolis Hastings sample.
About what?
Metropolis Hastings.
Oh, yeah.
sample.
Oh, someone's asking me about the technical bit.
So, in your experiments, what the probability of acceptance sort of look like?
Yeah, it can be very low in some of these data sets because a lot of these polyetic data sets are actually defined on relatively few nodes, but they have tons of edges, right? So the Enron email corpus has, I want to say 150 nodes, but on the order of 10,000 hyper edges. And that means there are lots of parallel edges in the data set, and that means that this acceptance probability can get quite low. It can be on the order of, let's say 1% in many cases. That said, I have yet to find a case that really was not practical to randomize using this algorithm. When I was doing these experiments, the bottleneck was actually randomizing the dyadic projected graphs, not randomizing the hypergraphs, which makes sense, right? Because when you have these polyadic data sets and you project them, you add a ton more edges, right? You're adding combinatorially more edges to the graph. It's going to be harder to randomize. So that was always the bottleneck for me.
When you're talking about thinking about dynamics on hypergraphs, do you have a sort of toy motivating example for that? Because in my mind, there's some, like, you can look at the flow of ideas and collaboration groups, but that seems like a very challenging, big question that I'm sure there's easier ones, but maybe
I think that would be fun.
fun.
You can certainly do that. You can sort of start with simple epidemic models, simple various SI, SIR, SAS models, see how those propagate, and then go from there. I think there's definitely a challenge connecting those to data science, right? Like you can start with sort of physics type theory, and then connecting to data science is harder. I think probably you can use random null models to sort of get at both, but they won't solve the problem of how to actually connect the two together. But as people here know, that's a hard problem in general and worth a lot of work.
Sort of related to that is that I just don't have a good intuition about like expected properties of hypergraphs that we encounter in real life. Like, does there tend to be characteristic edge number distributions and as well as degree distributions, or?
Yeah, it can really vary across the data sets, right, in the domain. So what Austin Benson provided has a wide range of different application areas which predictably have different properties, right? So for example, in the congressional bills data set, that I think the typical bill in that data set has about 8 co-sponsors, whereas in something like the high school interactions data set, a typical edge has just a little bit more than 2 nodes attached to it on average. So all these properties can vary quite extensively across application areas. One study that you can kind of see hints of this in some of Mark Newman's early work on collaboration networks, for example, actually doing sort of comparative descriptives of networks in different domains. You could certainly do something like that for hypergraphs as well. I'm not sure if you would necessarily need or want null models for that. I could sort of see versions of that paper that would work well both ways. Of course, the thing about these null models is that they're maximally boring, subject to the constraints that you give them, right? They're entropy maximizers. So they're not going to display, they're kind of designed not to display interesting structure other than what you bake in with the dimension sequence and the node degree sequence.
First, I'll say, great point. I'm glad you brought up at the end that you're looking into like which projection should you use, because that was the question. That was the one annoying thing I had was, well, what if we projected make it the weight 1/6 instead?
Yeah.
Assumedly close, but it's not that pretty. So
yeah, you can do that, and as it turns out, that will turn out to, in the assortativity case, that will turn out to get you the same answer as this hypergraph Spearman assortativity coefficient. What it won't do is solve your randomization issue.
Exactly.
Yeah.
Thanks. So first off, good point at the end there. Would you mind speculating a little bit?
I never mind speculating.
If it would be possible to define a clustering coefficient for polyadic data, because I mean, yes, clustering, the way it's defined in terms of like triangles over stars, over P star is very very dyadic, but that doesn't mean that there might not be a definition of clustering that if you only have 2 edges reverts back to that definition, or even maybe that's too contrived of a definition for some more general phenomena.
Yeah. So one thing you could certainly do is say, well, I'm going to consider triples of nodes, and I'm only going to count sort of possible triangles when I think of the triple being connected by 2 distinct hyperedges, and then there needs to be a third distinct hyperedge connecting them. That kind of thing you can absolutely do mathematically. I don't know. Again, I'm not sure exactly what application would motivate that particular definition, but it certainly works. You can certainly measure it. Another thing that I think is actually a bit related to this is there's this recent work in simplicial closure and simplicial correlation. And no one has actually given a very precise definition of what they mean by simplicial closure, but one idea is roughly that hyperedges should correlate and overlap more than you would expect them to, and that's a certain kind of clustering.
Set overlap?
Yeah, set overlap kind of deal. Actually, I'm not going to launch into that, but this is something I've also been thinking about. So you can actually sort of look at edge intersection distributions and say, okay, well, to what extent, we know that these hyperedges overlap a little bit because the configuration model at least is going to force them to overlap on individual nodes. But maybe we're going to see lots of hyperedges that actually overlap on 2 nodes in the actual data, or 3 or more nodes. That kind of thing you can actually look into and sort of get a sense for how densely, I hesitate to say clustered because that does have this technical definition, but roughly, yeah, like how much hyperedges are correlated with each other, how much we see this kind of set overlap. It's not exactly the same thing as the triadic closure, but I think it expresses a related idea that's been receiving a lot of attention in the polyadic networks literature lately.
Some intuition why just a modified hypergeometric distribution doesn't hold hyperedges?
Modified hypergeometric.
Right,
Sorry.
so you would want to have a regular hypergeometric distribution splitting your nodes into sets, right? It's a typical ERN problem.
Mhm.
But then you don't want multiple stubs from the same node all into the same edge. That was your extra criteria. So you can subtract out all configurations in which the same node appears multiple times within an edge. So why doesn't that just capture the distribution graphs that one can generate?
The distribution for
Graphs that one can generate
Um,
on paper.
so sorry. So what is the random variable that you're suggesting should be hypergeometrically distributed?
So I'm thinking about the ensemble of random graphs
Yeah.
that you're sampling from.
Yeah.
And that ensemble just respects a typical ERN placement scenario in which each node has multiple placements, right? So you can kind of add a stub for each node or replicate nodes
Yeah.
multiple times, place them into the ERNs
Yeah.
according to hypergeometric, and then you're rejecting scenarios in which the same node stub has occurred within the ERN
Yeah.
multiple times.
So that construction will okay. So let me first say that that construction will get you a stub-labeled configuration model, which is a good model because you implicitly distinguish all the stubs. Perfectly good model. That is not the one that I've been using here. The vertex-labeled configuration model does have different properties because it's essentially saying, well, all the stubs are interchangeable, whereas the stub-labeled model distinguishes the stubs. So you will get different probability distributions that way. That said, it's a good model, and I don't think that I currently see what random variable should be hypergeometrically distributed in that model. But what is true about that stub-labeled model is that you can get many more analytic results about its moments. You can say this is asymptotically distributed this way, the degrees, the intersection distribution. So if you sort of like proving asymptotic theorems about the moments of distributions, the stub-labeled model is a really good one. And so maybe we can talk offline about the hypergeometric point. It's a good model. That paper by Fosdick and collaborators is a lot more detailed about what the difference is between stub labeling and vertex labeling. So I'd also encourage you to kind of look into that if you haven't already.
Any other questions for Phil?
I'm going to hang out for a little while if no one wants to
Here for a
chat.
while.
Yeah.
Okay, thanks, Phil. Thanks, everyone.